Hello, and I'd like to go over a proof. This is from the textbook, and this proposition says for matrices A, B, and C, the quantity A times, in parentheses, B plus C is equal to the quantity A times B plus the quantity A times C. So as we go through this proof, I want to go over kind of the thought process, because when you're reading or watching somebody's proof, it's very hard to know how it was constructed. So in this case only, I'm going to give you the entire process of constructing this proof and understanding how we're going to go about it. Now this might look familiar to you because it looks just like the distributive property for real numbers. In fact, it is the distributive property. So you might say, oh, we can just distribute in the A into the parentheses, and then we get the result. But we know that's true for real numbers. We have to prove that it's true for matrices. Which is not something that is inherently obvious, but it seems like it should be true. So I'm going to go through the forward-backward method, and then by doing that method, we'll kind of go backwards and see what definitions we're going to need to prove this. So first thing is to identify what is my hypothesis and what is my conclusion. So using the other videos, I know that we're kind of using the same letters a lot here, but I'm just going to call it A. And that is what I'm assuming in this case. And then B is going to be what I'm trying to prove. So what do I know? What are my hypotheses? Well, I know that A, B, and C are matrices. And I know that all of the sums and products are defined, which means they exist. There's no dimension mismatch. So we can go ahead and assume that sums, in this case it'll be B plus C, and also AB plus AC, and the product A in parentheses B plus C, and the products A, B plus C, AB, and AC exist. Because if they don't exist, then we can't find the next part. And then B is exactly what we're trying to prove. That is already given in the problem. A times the quantity B plus C is equal to AB plus AC. Okay, so using the forward-backward process, I want to think about what would I do. So for statement B down here, what is a statement that if I know that statement B1 is true, then statement B must be true? So what are we trying to show here? We're trying to show that two matrices are equal. So our leading question is, how do we show that two matrices are equal? We can show that two matrices are equal if they have the same size and all of their corresponding elements are equal. So I'll just put that in abbreviation here. Same size and all corresponding elements are equal. So from here we can get our statement B1. Our statement B1, which we would have to prove before B, right? B1 would be to show that A, B plus C, and AB plus AC are the same size and corresponding elements are equal. Okay. So if we could go backwards from there, or we can kind of see what happens if we keep our assumptions. We know that A, B, and C are matrices, and then the sums are defined and the products are defined. They exist. So we're going to have to just pick some sizes here. So this is not part of the proof yet. This is just kind of understanding what we need to do. Let's say that A, we're just going to pick two dimensions. Let's say it's m by n. And because I said in my assumption that AB and AC exist, that means that B has to be something like n by p, because for a matrix product to exist, their inner dimensions must be the same. And then we know that when we add AB plus AC, that sum exists. And the only way that would exist is if A times C is the same size as A times B. So that means C must also be an n by p. A is an m by n. So the product AB must be m by p. And then AC is also m by p. So that means I know that AB and AC are the same size. But even though two matrices are the same size, it doesn't mean that they're equal. And then the product A times B plus C, the product A times B plus C, if we add two matrices that are the same size, the resulting matrix is also the same size. It's an n by p, and then A is m by n. So the product A times B plus C must also be m by p. And then if we add AB plus AC, the matrix that we get will also be m by p. So I've really just shown that these two matrices must be the same size. But we haven't done our proof yet. So if I show they're the same size, I also have to show that all corresponding elements are equal. And there's a definition for that. So this is from the book. So this is something I can show from my assumption. I know the sums and the products exist. So we can call this next one our statement A1. And that'll come after A. From A1, we want to show that two matrices are equal using the definition. Using the definition, A equals B means that for A, and this is called an IJ argument, just breaking up a matrix A into all of its elements in row I, column J. So that just represents every number in the matrix. And B is equal to Bij. Then I Aij equals Bij is true for I between 1 and m, if it's a m by n matrix, and for j in between 1 and n. Okay, so if I can show that A1 is true, I would have to show that every element on one side of the matrix is the same as every element on the other side of the equation in the matrix. So my outline of my proof, this is my outline. So I kind of did my rough draft here. My outline of the proof is I start with my assumption, which is A. A is saying that I have 3 matrices, and those sums and products, as I mentioned before, are defined. And then what I want to do from A is I want to show A1, and essentially I want to show that the product A times B plus C equals AB plus AC. I want to show that every element in the matrix on the left is the same as every element on the matrix on the right, and that's where it matches up with B1. How do you show that 2 matrices are equal? If every element in one matrix is the exact same as every element in the second matrix, and the 2 matrices are the same size. And then once I show they're equal, then I have statement B. Okay, so let's prove it. Here's the proof. So there's still some more details that we are not going to get into before the proof, especially if you've learned stuff about sums, maybe from calculus. We're going to split a sum and do some properties with real numbers, but those are all things you should have learned before this class. So we'll get right into the proof. So the first thing we're going to do with our proof is we're going to create, using the left-hand side, this one right here, we are going to write that in the IJ form. And how can we do that? By the definition. By the definition of the IJ entry of a matrix, we can turn the product A times B plus C, and then put a little IJ to the next, to the right of it. I can write that as a sum, and we use the big sigma notation. This is in the book, the definition of the sum. Define the elements in a matrix product. And I should say here a matrix product. That is equal to, if we sum it over all the k's from 1 to n, whatever the size of our matrix is, that's going to give us, I'm just going to turn A into its IJ form. In this case, since it's not IJ, it's IK. And then that's going to be multiplied by the IJ form of capital B, which in this case will be PBKJ. The K's have to match so that the inner matrix product exists, plus CKJ. So all I did was I converted it from a matrix to the individual IJ form for the sum to create the product. And then what we can do is we can take that product and just use the distributive property. How come we can use the distributive property now and I couldn't use it before? That's because that the lowercase a, b, and c, these are just real numbers. And with real numbers, we know we can use the distributive property. So we're going to use the distributive property. And if we distribute that in, That is equal to the sum from k equals 1 to n of aik times bkj plus aik times ckj. Okay, now it's starting to look almost like the right-hand side over here. So I've just turned it into the ij form, and then now I basically just have to turn this into ab plus ac, and then we know, because the equal signs are there, that they're going to be the same. Okay, we can do something with a sum like this. We can split the sum. Splitting the sum means we break it up into two parts. So this sum is equal to the sum from k equals 1 to n of a, I, k, b, k, j plus the sum from k equals 1 to n of a, I, k, c, k, j. And we should recognize that by using the definition. We can repeat it again here using the definition of the ij entry of a matrix product. This is really the same thing as a, b, ij plus a, c, ij. So we've just shown that the original one up here was a, b plus c, a times the product b plus c, is really the same thing. All the elements of that matrix are really the same thing as adding AB plus AC, and that's really equal to AB plus AC. Thus, A times the quantity B plus C is equal to AB plus AC. When you finish a proof in math, different authors do something different. You can draw a little box down here, which means the proof is done. Nice to just kind of end your proof that way. Another common thing people do is they write QED, and this stands for, I believe it says, I know it translates to that which has been demonstrated. Quiero demonstrato, something like that. That in which has been demonstrated. But there's your first proof. I hope it makes sense, and the proofs that you're going to conquer in this assignment will be very similar.